Hello grade 10, last time we explored the arithmetic number sequence wherein it goes from one term to the next by always adding or subtracting backward the same value. I will show you something. I took this when I went to Palawan Pera Padala. Here's the picture. Is the additional fee in sending a particular amount follows an arithmetic sequence or not? It's for you to find out. Today, it's time to face the second special kind of sequence. Watch this video.
There once was a poet who fell upon such hard times that he was no longer able to feed his family. So he decided to set out for the palace and appeal to the generosity of the king. Upon being summoned by the king, he started reciting his poems. The king, well pleased, asked him to name his reward. Pointing to the finely wrought chessboard, the poet said, "Your Highness, if you place just 1 grain of rice in the first square and double it for every square, I will consider myself well rewarded." "Are you sure?" asked the king. "Just grains of rice and not gold?" "Yes, Your Highness." "So it shall be." So the courtiers started placing the grains of rice. 1 on the first square, 2 on the second, 4 on the third, 8 on the fourth square, and so on. By the time they came to the 10th square, they had to place 512 grains of rice. By the 20th square, the number swelled to 5,24,288. When they came to the halfway mark, the 32nd square, the grain count was 214 crores, 74 lakhs, 83,648. Soon the count increased to lakhs of crores. Eventually, the hapless king had to hand over his entire kingdom to the clever poet. And it all began with 1 grain of rice. Moral of the story? Never underestimate the power of compounding.
Whoa, amazing, right? But is it really possible? Just starting a single grain and doubling it will reach an enormous amount? Let's have a simple experiment for this. I want you to get a 1-whole sheet of paper or a bond paper and try this simple activity. Fold the paper in half, open it up, and count the number of rectangles formed. Record your answer in this table. Keep on folding in half and keep on counting the rectangles to fill up your table of values. Can you see the pattern in the number of pages formed? How many pages can be formed on the 10th fold? How many times can you manage to fold it? Can you do the 8th fold? Let me try it. Guys, FYI, the long-standing challenge was that a single piece of paper, no matter the size, cannot be folded in half more than 7 or 8 times. Until Brittany Gallivan, a 16-year-old lady, has solved the paper folding problem. Wow! She managed to continue folding until 11th or even 12th fold. What? How did she do it? Let's watch this.
How many times can you fold it?
4. Getting tricky.
I think that's about it, really. 6.
For the 7th one, I might need a hammer.
Crazy as it may sound, it's mathematically impossible to fold a sheet of A4 paper like this in half more than 7 times. The problem is, every time I make a fold, the paper shrinks in length and doubles in height. This is happening at what's known as an exponential rate. With each new fold it doubles again, and very quickly I run out of paper. If you want more folds, you need more paper. And to find out how much more paper, we need a clever calculation. In 2002, 16-year-old Californian Brittany Gallivan came up with an equation which tells you how much paper you need to make a given number of folds. She used that equation to set the record for folding paper, 12 folds. To find out more, I'm meeting mathematician Dr. Nicolette Rattenbury.
So L is the minimum length of paper that we're going to need to do these folds. We've got T, which is the thickness of the paper that we're working with, and here we've got N, which is the number of folds that we want to be able to make.
I want to try and beat Brittany's 12 folds. So how much paper will I need to make 13?
Our thickness is 58 millionths of a metre.
Okay.
And we're going to have to increase our N by 1, so we're now going to have 13.
Oh, this is going to be a big number, isn't it? The equation tells us we need more than 2,000 metres of paper. But to be safe, we're going to use more.
I'd probably suggest using 3,000 metres.
That's nearly 2 miles of paper. It's an epic amount of paper. Now we need somewhere equally epic to fold it.
Compare these two number sequences. What have you observed? If you examine it closely, the first number sequence uses a common difference of 2. We just always add 2 to the previous number all the time. The first difference is a constant, therefore it's a linear pattern, and we called it an arithmetic sequence. When we graph it, it forms a straight line. The second number sequence is far more different. It's not adding 2, it's multiplying by 2 to the previous number. What do you think is the shape of its graph? Does it look familiar? This is the number sequence in our chessboard story in our paper folding activity, right? We call this a geometric sequence or geometric progression. Geometric because it is like increasing the dimensions in geometry. A line is one-dimensional and has a length of r. In 2 dimensions, a square has an area of r squared. In 3 dimensions, a cube has volume r cubed, and etc. And yes, we can have 4 and more dimensions in mathematics. So by definition, a geometric sequence is a sequence where each term after the first is obtained by multiplying the preceding term by a non-zero constant called the common ratio.